Hello everyone! The purpose of the Black Hole Orbit Lab was to observe the change in position of a fictitious star due to the gravitational pull of a fictitious black hole, and to then use a momentum principle and Newton's law of universal gravitation to calculate the mass of the black hole at every 86,400 seconds for one complete rotation of the star's orbit. I found the average mass of the black hole to be approximately 1.9901 to the 31st power kilograms, which is more than the combined mass of 10 suns. We know that the net force is equivalent to the change in momentum over change in time, and although these two components have the same numerical value, they're derived in different ways. The net force is a summation of the interactions on a system, whereas the change in momentum over the change in time is the effect of these summated interactions on a system. The net force can be broken up into the net forces in the perpendicular direction to the path of motion and the net forces in the parallel direction to the path of motion. Likewise, the net force in the parallel direction is equivalent to dp dt in the parallel direction, and F net perpendicular is equivalent to dp dt in the perpendicular direction. Using Newton's equations for universal gravitation, I was able to manipulate it to isolate the unknown mass, i.e. the mass of the black hole. We already know the universal gravitation constant, and we're given the mass of the star, and we can calculate the magnitude of our position vector by subtracting the star position vector from the black hole position vector. And we know that the magnitude of the force of gravity is equivalent to the magnitude of the net force because we're told that this force of gravity is the only force acting on the system. Now I'm going to bring my code up to show it to you. And here you can see my module running. This black arrow is the net force in the parallel direction. The blue one is the net force in the perpendicular direction. And because the net force in the perpendicular direction is always pointing to the center of the kissing circle, we know that the black hole would be somewhere down here. And then this is the net force combined. You can see that all of the masses calculated at each point are very close to one another, thus showing that there is a low standard deviation. To answer the what if question, I've typed it out again right here. If the motion of the observed star remains unchanged, and thus the magnitude of dp dt is unchanged, and therefore the magnitude of the net force is unchanged, ergo the magnitude of the force of gravity is unchanged as well because they all equal one another, then the mass would be the exact same. For the magnitude of the force of gravity of the new black hole to be the same, the magnitude of the position vector would have to be identical as well. So the new black hole and the star would have to be at a distance proportional to the distance between the original black hole and the star. But the new black hole would not have to necessarily originate at the exact same location as the original black hole. Thank you very much for watching my video.